Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3rd, 2026, just 1 week ago. It introduces the first agentic framework capable of automatically generating high-quality scientific illustrations from long-form text, achieving a 67% publication readiness rate, according to domain experts. The paper is titled AutoFigure, Generating and Refining Publication-Ready Scientific Illustrations. And as we'll see later, the results demonstrate a remarkable ability to balance structural accuracy with aesthetic appeal in a way previous tools could not. And for those interested in the implementation, the authors have shared their code on GitHub. Well, to build a system like AutoFigure, you first need a solid benchmark. Table 1 presents a comprehensive analysis of Figure Bench, the dataset created for this study. It contains 3,300 text figure pairs in total, sourced largely from scientific papers, but also including blogs, surveys, and textbooks. Notice the text tokens column in the middle. It highlights a massive variation in context length, ranging from over 12,000 tokens for papers down to just 350 for textbooks. This diversity forces the model to handle both extremely long, detailed contexts and shorter, more concise inputs. So while the previous table listed the statistics, Figure 1 illustrates the actual composition of Figure Bench. The top half displays examples from scientific papers, such as Cycle Researcher or Deep Review, where the input is a dense abstract and the output is a complex architectural diagram. Then, the bottom section expands into other domains. On the left, we see textbook examples, like the waterfall model, while the middle and right show surveys and blogs, covering topics like video understanding and off-policy learning. This mix is crucial because it tests the system's ability to adapt to different visual styles and content depths. Alright, having established the dataset, Figure 2 reveals the architecture of the AutoFigure framework. The system operates in 3 distinct stages. First, the blue concept extraction panel shows a vision language model agent converting unstructured text into a structured symbolic blueprint. Next, the orange panel details the critique and refine stage, where an AI designer and critic optimize the layout for alignment and balance. Finally, the green rendering strategy stage synthesizes the image, utilizing an erase and correct loop to replace blurry text with crisp labels using optical character recognition. The authors even note that this figure itself was generated by the tool, serving as a direct proof of concept. So, Figure 2 detailed the architecture. Now, Table 2 presents the comprehensive user evaluation results across 4 domains: blog, survey, textbook, and paper. The study uses blind pairwise comparisons to calculate the win rate, shown in the far right column, which measures how often human experts preferred the model's output. AutoFigure dominates here, achieving remarkable win rates of nearly 98% for textbooks and 75% for blogs. Even in the highly technical paper category at the bottom, it secures a 53% win rate, significantly outperforming baselines like GPT image, which often fails on content accuracy. Well, while Table 2 showed broad win rates, Figure 4 asks the actual paper authors to judge illustrations of their own work. In Panel A, the overall win rate analysis shows AutoFigure achieving an 83% win rate, far surpassing the next best baseline. Panel B tracks publication intent, and here, authors confirmed that nearly 67% of AutoFigure's outputs were ready for immediate publication. Finally, the bottom charts confirm this superiority, with the model consistently scoring above 4 out of 5 on accuracy, clarity, and aesthetics. So while Figure 4 confirmed the high-level success, Figure 5 now dives into the ablation studies to understand what drives that performance. Panels A and B compare different backbone models, like Claude 4.1 Opus and GPT-5, both before and after the rendering stage. These charts show that strong underlying models are critical for generating robust initial symbolic layouts. Then Panel C illustrates the impact of test time scaling. As the number of refinement iterations increases from 0 to 5, the overall quality score climbs steadily from roughly 6.3 to over 7. Finally, Panel D evaluates the intermediate sketch formats. It clearly shows that using SVG or HTML codes yields far better results than PowerPoint formats, likely due to their precise structural definitions. While Figure 5 analyzed the component contributions, Figure 6 offers a qualitative comparison using the famous InstructGPT framework as a test case. Panel A displays the original human design, detailing the 3 steps of reinforcement learning from human feedback. In contrast, baselines like Diagram Agent in Panel B or GPT Image in Panel C struggle, producing either oversimplified chains or crowded, illegible text. However, the AutoFigure output on the far right is striking. It accurately regenerates the complex three-stage process with clear typography and distinct visual artifacts, effectively matching the standard of the original publication. Wrapping up, 2 takeaways stand out. The creation of FigureBench provides a much-needed standard for this domain, while the AutoFigure framework demonstrates that I can genuinely master scientific illustration. By combining reasoning with rendering, it enables automated systems to communicate complex discoveries visually, potentially saving researchers countless hours of design work. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.